Hi guys. Wait, are we back? Yeah, we are back. We're back. Oh, finally. Thank God. Thank God. Yes. This was a sad moment. This was a sad moment. Yes. Okay. Guys, quickly go and call up your friends, everyone. They should know that we are taking the session here. Quickly go and call up your friends and let us not waste any more time. Let us go ahead. What do you all say? Yes? So we were talking about hybridization. So we bacha, today we have a very little time and I do not want to talk about MV self scholarship right now. How about I can you can comment it in the you can comment it after the chapter is over, and then I can ask my team to get back to you, and we can solve your issue, but not right now. Can we please do that? Yeah, thank you so much. So guys, without wasting a minute, everybody, let us get on with what we were doing now. So if steric number is 5, then we know that we have one s orbital and 1 2 3 p orbital plus 1 d orbital, which will be sp3d hybridization, and we will get trigonal bipyramidal. Now if steric number is 6, then what do we get? If steric number is 6, then we get 1s orbital plus p plus p plus p plus 2d orbitals, and then we will get sp3d2 hybridization, which will be our octahedral geometry. Yes, it will be octahedral geometry. And finally, we come to steric number 7, when we will have 1s plus p plus p plus p plus d plus d plus d is equal to sp3d3 hybridization, which will be, somebody had told me this. Yes, this will be pentagonal bipyramidal, right? This will be pentagonal bipyramidal. Very good. Yes, well done everybody. Great, amazing. Do we all understand this? This was easy peasy biryani tasty. Great. Now let us talk about each and every hybridization. Okay, what do? We are going to talk about each and every hybridization now, one by one. Are you all ready, guys? Are we all ready? Are we all ready? Quickly go and call up your friends, everybody. Thank you, Shakti. Thank you so much. Thank you so much. Thank you, Sobi. Thank you so much for supporting what I suggested. Chalo. Now, let us talk about SP hybridization. Okay, let us talk about SP hybridization. When we say SP hybridization, that means that our steric number has to be what? Our steric number has to be 2, right? Yes, we have just seen that, isn't it? See, steric number 2, SP hybridization. And remember, what was the example that we have taken? What was the example that we took? BeCl2. Do you remember? BeCl here, Cl here, and this will be the bond. Here we will see 1s, 1, 2s orbital, and there will be a 2p orbital. Together they will form sp hybridization, isn't it? Together they will form sp hybridization. Very good. Now if I ask you about N2, yes, let us talk about N2, dinitrogen. What about dinitrogen, everybody? Dinitrogen, we all know that it forms triple bond with another nitrogen, but we know nitrogen has how many electrons in the outermost shell? 5. So here we will have one lone pair, here we will have one lone pair. Acha, now calculate the steric number here. Calculate the steric number here, everybody. How many lone pairs? See, near to, okay, everybody, just have a look, guys. Have a look, everybody. Have a look. Understand this. This is our nitrogen. This is our nitrogen. Near to this nitrogen, which is the surrounding atom. The surrounding atom is this. So it has only one surrounding atom, and it has here one lone pair. So that means that I can write it as one lone pair plus one surrounding atom. Our steric number becomes 2. Steric number becomes 2. And now if steric number is 2, that means what will we get? We will get sp hybridization, isn't it? Yes. So this is how you draw for nitrogen. Similarly, you will get it for CO2 as well. Okay. All right. CO2, for CO2 also we will get sp hybridization. Clear here, everybody? Now let us go to Now let us go to sp2 hybridization. Shall we, everybody? Let us have a look at sp2 hybridization, my dear bachos. For sp2 hybridization, bf3, we have taken the example of bf3 couple of times. I do not want to take bf3 once again. Shall we have a look at so2? What do you see? What do you say so2? Let's have a look at so2. So2. So too. So we will have central atom will be our sulfur, right? And we can clearly see that this oxygen does not have any charges. That means it will form double bond O, double bond O. But now sulfur has how many electrons in its outermost shell, guys? Sulfur has how many electron? Yes, sulfur has how many electrons, everybody? Sulfur has how many electrons in the outermost shell, everybody? 1, 2, 3, 4, 5, 6. So there will be one lone pair here, right? Now if I ask you to calculate the static number, will you be able to do it? Yes, you will be able to do it. How many lone pair is there? You have one lone pair here. How many surrounding atoms are there? There are two surrounding atoms. So one lone pair plus two surrounding atom is equal to 3. If steric number is 3, that means our hybridization is definitely sp2 hybridization. Make sense it, everybody? Yes? Do we understand this, guys? Do we understand this? Clear? Great. Okay, now moving on. Let me draw a line here and let me take care of sp3 hybridization. Chalo. Let us talk about sp3 hybridization, everybody. What will happen to sp3 hybridization? Any example, guys? Any example of sp3 hybridization? Anybody? Any example of sp3 hybridization? Let us take xenon, XeO4. What do you all say? XeO4. If we take again, see, O4, there are 4 oxygen and all of them are neutral. So what will happen is we will have xenon here, we will have double bond oxygen, double bond oxygen, double bond oxygen and double bond oxygen. Now what do I see? Steric number is going to be 4 surrounding atom. Is there any lone pair? Do you see any lone pair, everyone? No lone pair. If there are no lone pair, then I am going to write here 0 lone pair, which is equal to 4 steric number. That means sp3 hybridization. Another example, everybody. Let us take a look at NH3. What do you all say? Let us take a look at NH3, everyone. NH3 if I take, so you have N here, hydrogen, 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 right? Hydrogen, hydrogen, hydrogen. How many lone pair? One lone pair. That's it. Steric number is what? Steric number is 4. If steric number is 4, that means what will you get? What will you get? sp3 hybridization. Acha, now if I rub this part, now you will get the shape. This was your molecular geometry. This was your molecular geometry. Everybody have a look, guys. Have a look, guys. Now if I cover this lone pair, do you get the shape? Do you understand the shape? Without this, it's the molecular geometry. The molecular geometry is tetrahedral. But if I cover this, what do you get? You get pyramidal shape. What do you get? You get pyramidal shape. What do you get? Pyramidal shape. Write it down in the chat box, everybody. Quickly write it down in the chat box. Quickly write it down in the chat box, everybody. Yes? Quickly, guys, I need to see the chat. I need to see the chat, everybody. Are you all here? Very good, very good, very good. Well done. Yes, awesome. Okay. So sp3 hybridization, sp2 hybridization. Are we understanding all of these? Can I get some easy peasy biryani tasty, everybody? Can I get some easy peasy biryani tasty? EPBT, everybody? Can you guys tell me some EPBT? Give me some EPBT, guys. Very good. Chalo. Next one. Now we are going to include our sp3 dehybridization. Shall we do it? Chalo. Let us once again I'm going to draw a line here. Yes, and now let us go and understand sp3 dehybridization. Okay, let us have a look at sp3 dehybridization. Should we take the example of xenon compound we have taken, right? Let us take a look at XeO2F2. What do you say? Let's take a look at XeO2F2. If we do this, then what will happen? So we will have a xenon here, right? Xenon here. Now the fluorine, okay, let us attach the fluorine here. Now we will keep the double bond oxygen here, double bond oxygen here. After this, do we still have a lone pair? Yes, we do. Yes, we do. We still have a lone pair here, my dear bachos. Now calculate the steric number, everybody. Calculate the steric number. How many surrounding atom do you have? You have, for xenon, everybody, you have 4 surrounding atom, plus you have one lone pair, which is giving you 5 as a steric number. If it is steric number 5, that means sp3d hybridization. Yes. Now if I talk to you about, if I tell you that we want to find the shape of PCl5 will come, bacha, PCl5 will come, chill, PCl5 will come. Let's say that we want to take, what do we say, SF4, yes, SF4, right? SF4, let's do for SF4. SF4. For SF4, how do we draw it? See, we will have a sulfur here. Right here we will have a lone pair, and then we will have all the fluorine atoms like this, okay? All the fluorine atom like this. Now, bachos, this, if you look at it, once again, if you calculate, you have 4 surrounding atom plus 1 lone pair, that will give you 5 as steric number. 5 steric number will have sp3d hybridization. And now tell me, everybody, if I take this whole thing, okay, if I take this whole thing, and if I let's say that if I rotate it like this, do you think that this looks like a seesaw shape? Do you think that this looks like a seesaw shape? If I cover the lone pair here, if I cover the lone pair, does it not look like a seesaw? Does it not look like a seesaw? It does, right? It does, isn't it? Yes. So this is your seesaw shape. However, what is the geometry, bachos? What is the geometry for sp3d hybridization? We have just noted it down. For sp3d hybridization, it is going to be trigonal bipyramidal. Clear hai, everyone? Clear hai, guys? Everybody? Are we all clear with this? Yes? Hello, everybody. Welcome to the session. Welcome. Yes? EPBT? Great. Now, moving on. After sp3d, what do we do? After sp3d, we have sp3d2 hybridization. Chalo. Yes, sorry. We have sp3d2 hybridization. Okay? sp3d2 hybridization. For this, let us take the example of, what do we take now? Let's take another xenon compound. Let's take Xe, okay? O6, 4 minus. XeO6, 4 minus. What will this, how will this look like? So you will have Xe. Now you see you have 6 oxygen, right? 6 oxygen. So 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5 and 6. All the 6 oxygen we have noted down, right? Now have a look that here we have 4 negative charge. This 4 negative charge, can we distribute it? We can distribute it, right? So we can write here 1 negative, another negative, another negative. But these two, they do not have any other negative charges. There are no negative charges right here. So here we will draw another double bond and another double bond. And yes, everybody, SF6 is also going to be the same. But SF6 will have no lone pair, but it will still have sp3d2 hybridization. Am I clear, everyone? Am I clear with this? Am I clear with this? This is clear, sp3d2. Chalo, next let us go for sp3d3 hybridization. Okay, sp3d3 hybridization. Chalo batao. sp3d2 hybridization will obviously be, molecular geometry is octahedral. Here the shape is also octahedral, by the way. Yes, because there are no lone pairs, the shape is also octahedral. But if there was any other if there was any other lone pair, then it would not be octahedral, it would be of a different shape. Chalo. Now let us move on and let us have a look at sp3d3 hybridization. sp3d3 hybridization, let's have a look at it here. IF7, right? We have taken the example of IF7 in the beginning as well. So you have I, 1, 2, 3, 4, 5, 6 and 7. So you have IF7. You have IF7. Find out the steric number. The steric number will obviously be 7. If it is 7, then you get sp3d3 hybridization. Am I clear, guys? Am I clear, everybody? Am I clear, guys? Yes? Okay, great. Now that you have understood this, now if we go and do this, will you understand? See, for SF4, the molecular geometry was trigonal bipyramidal. However, the shape of the molecule is seesaw. Do you remember this? Yes. If I take the example of ClF3, for ClF3, how are you going to do, Bachu? ClF3, see Cl, 1, 2 and 3. The F and F you have put up, but chlorine still has 4 more electrons left. So what will happen? Here you will have 2 electrons. Here you will have 2 electrons. Now this is actually not exactly T-shape. This lone pair tries to repel this. This lone pair tries to repel this. So you get a bent T-shape for ClF3. Are you guys getting it? Are you guys getting it, everybody? Chalo, more guys, more guys. BRF5. BRF5, if you calculate, yes, bromine also belongs to group 17. Group 17 bole to there are 7 electrons in the outermost shell. This is combining with 5 electrons, but you will still have a lone pair, and this will become, see, the molecular geometry is octahedral, but if you do not look at the molecular geometry, if you do not look at the lone pair, then what happens? This looks like a square pyramidal. This looks like a square pyramidal, isn't it? How does it look like a square pyramidal? See, it will look like this. See, square, F5, right? So fluorine, 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 and here is another fluorine. This is where the lone pair is. So together, this looks like a square pyramidal, does it not? Does it not look like a square pyramidal? This is how it will look like a square pyramidal. Got it? Clear? Great. Moving on. See, for XEF4, you still have a lone pair here, you have a lone pair here, although the geometry is octahedral, but if you do not look at the lone pair, you will have square planar shape. Is this clear, everybody? Is this clear? How to denote or how to determine, figure out the shape and the molecular geometry. Will you all be able to do it with the help of the steric number? I believe you can easily find the hybridization. The moment you find the hybridization, you can figure out the shape, you can figure out the molecular geometry, and then from there your questions are going to be super easy, right? Yes, everybody. All of these I believe that I have already taught you. Now quickly let us try and do a question. Are you all with me? Shall we solve a question, guys? Let's solve a question. The question is molecular shapes of SF4, CF4 and XEF4 are. The options are the same with 1, 1 and 1 lone pair of electron respectively, or the same with 1, 0 and 2 lone pair of electrons respectively on the central atom, or is it different with 0, 1 and 2 lone pair of electron respectively on the central atom, or is it option D, different with 1, 0 and 2 lone pair of electrons respectively on the central atom? Chalo, let us try to solve it for SF4, right? SF4. So if I draw the structure here, everybody, I think you all will understand. You all will understand, isn't it? Yes? Shall we draw the structure, guys? Shall we or not? Are you all with me? Chalo. For SF4, everyone. Now, sulfur has how many electrons, everybody? Sulfur has how many electrons in the outermost shell? Sulfur has 6 electrons. So here you have surrounding atom 4, right? So you have 4 surrounding atom, but obviously because you have 6 electrons, that means there will be 1 lone pair. So 4 surrounding atom plus 1 lone pair, steric number is equal to 5. If steric number is 5, what is the hybridization? The hybridization that you get here will be sp3d2 hybridization. Clear hai? Yes. What is going to be the shape? The shape here will be seesaw shape. We have just studied it, right? Yes. Now, let us talk about CF4. Let us talk about CF4. For CF4, everybody, this is carbon. Carbon is the central atom. If carbon is the central atom, how many How many number of electrons are there in the outermost shell? 4. So here if we want to calculate the steric number, there are 4 surrounding atoms and obviously 0 lone pair. You have 4 surrounding atom plus 0 lone pair. So 4 is the steric number. If 4 is the steric number, what will be the hybridization? sp3. If it is sp3, then bachos, how do you draw the structure? You draw it like this, 1, 2 and 3. This will be tetrahedral, isn't it? Yes, do we all agree, guys? This is going to be tetrahedral. Very good. Now, let us come to XEF4. It is XEF4, isn't it? It is XEF4. So for XEF4, everybody, let us figure it out. You have 4 surrounding atom, but we also know that xenon is a noble gas. That means it has 4 more electrons. Yes, it has 4 more electrons. So 4 surrounding atom plus obviously 2 lone pair we will have. That means our steric number is 6. If steric number is 6, then what will we have? We will have steric number 6, right? So 1s, we will have P3 and 4 plus D2. sp3d2 bole to octahedral. sp3d2 bole to octahedral. If it is octahedral, then how is the shape going to be? 1, 2, 3 and 4, right? So you will still have 1 lone pair here and you will have a lone pair here. Always remember, the lone pairs always has to be at the farthest, okay? The lone pairs has to be at the farthest. So here you will have F, F and F and F. So this will be the shape. So coming back to the options, what do you think is the correct answer? The correct answer is, of course, option number D. Option D suggests that 102 is the lone pair and the shape is also going to be different. Clear? Clear, everybody? Chalo, let us take a look at the next question, everyone. And the next question, oh, this is a JEE Mains 2018 question, everyone. The incorrect shape is represented by. The incorrect shape is represented by, everyone. Chalo, let's have a look at it. BF3. For BF3, surrounding atom is 3. That means that we will have what? Boron anyway has 3 atoms, right? Boron anyway has 3 atoms. So what will this be? This will be sp2 hybridization. Yes, this will be sp2 hybridization. sp2 hybridization will have what? It will have trigonal planar. This is definitely right. Now let's talk about NF3, guys. For NF3, what do we have? We have 3 surrounding atom plus we also will have 1 lone pair. We also will have 1 lone pair. So 3 plus 1 is going to be what? 3 plus 1. Steric number is 4. Steric number is 4. If steric number is 4, we will have sp3 hybridization. For sp3 hybridization, guys, what do we have? What is the molecular shape, guys? What is the molecular geometry? Sorry, what is the molecular geometry? Tetrahedral, isn't it? This is going to be tetrahedral. If it is tetrahedral, then why is trigonal planar written here? That means option B is our correct answer, or rather the incorrect shape. Okay, this is the incorrect shape. Okay, this is incorrect shape. Acha, by the way, molecular geometry is tetrahedral. Now everybody, NF3, right? See, this is going to be the shape, everybody. This is going to be the shape. So you have F, F and F, and here you will have a lone pair. So this will be your geometry. The geometry will actually be pyramidal. The geometry will be pyramidal, right? Yes, yes, this will be trigonal pyramidal. This will have trigonal pyramidal. The shape will be trigonal pyramidal. Geometry is a tetrahedral. Are you guys clear on what I'm trying to tell you? Yes, guys, are we all clear with this? Are we all clear with this, everybody? Yep, no. And the rest also you can check. ASF3. See, AS also belongs to nitrogen's group. Since it belongs to nitrogen's group, this will also have similar structure. Okay, chalo guys. Moving on to the next question, everyone. In a bonded molecule, the order of repulsion between the bonded and the non-bonded electrons. Ayo, this is super easy, isn't it? Lone pair, lone pair, lone pair, bond pair, and bond pair, bond pair. That means option C is the correct answer. Right? This is correct answer. Now, next question, everybody, is... Oh, we do not have a next question. Chalo, we will do next question later on. Now, let's talk about hybridization a little bit more. I think we have spoken about hybridization. This is something that we are done with, right, guys? Right? We have already spoken about hybridization before we got into the steric number and all of this. We are done with hybridization, correct? intermixing of the orbitals of slightly different energies so as to redistribute their energies, resulting in the formation of new. We're done with this? Yeah? We're done with this? We're done with this, right, guys? Isn't it? Yes or no? Bachos, tell me. Shri Chandana Trishya is also telling me. So we're done with hybridization. Great. Okay. All of these are done. sp hybrid orbitals, sp2, sp2, sp3, d2. All of these are done. All of these are done. Great. Okay. Okay. Let's do some more examples. Let's do some more questions then. Okay. How much marks in JEE Mains to get NIT Trichy Homestead? Ayo, ye boy, it's not there right on top of my head. I'll have to research for it and then come and tell you, okay? I'll have to research and then tell you. Acha, chalo. The bond angle in BF3 is everybody. Oh, come on. This is super easy, guys. Bond angle in BF3. In BF3, this is just a simple mathematic question. The correct answer is 120 degree. I mean, come on. Come on, right? You guys should have answered this. Chalo. As a result of sp hybridization, what do we get? As a result of sp hybridization, we get two mutually perpendicular orbitals? Not at all. Not at all. Do we get two orbitals at 180 degree? Yeah, we do. Yeah, we do. sp hybridization. One this side, one this side. Two orbitals at 180 degree. Absolutely. Option B is the correct answer. Next question. Which of the following statements is about hybridization, is true about hybridization? Only those atomic orbitals can be hybridized which do not differ much in shape. We don't talk about shape, right? We don't talk about shape. No, no. Only those atomic orbitals can be hybridized which do not differ much in energy. Yeah, that looks like the correct one. Yes. Told you, right? For example, I have taken as an example CH4, 2s and 2p. Now 2s and 2p are not very different, but I did not take 1s and 2p. Did I take that? No, I took 2s and 2p because they have comparable energies. They have comparable energies, everybody. All right, moving on. Acha, now shall we practice, everybody? Let us practice this because from here you guys get a lot of question, everybody. From here you guys get a lot of questions. So are you all with me? Shall we practice? Shall we practice? Yeah? Yes or no? Chalo, guys. You guys are able to see it, right? Okay, let's do it for BeCl2. How will the structure be? It will be BeCl and Cl, right? For BF3, how will it be? F, F and F, right? Like this. For SO2, you will have double bond O, and here you will have one lone pair, correct? Yes. For PCl5, somebody was asking me, ma'am, PCl5, ma'am, PCl5, ma'am, PCl5. Chalo, let's do for PCl5. So PCl5 will be somewhat like this. You will have a P here, right? And then on the axial positions, you will have one Cl here. Actually, let me draw it here. PCl5, right? PCl5, everybody. Let's have a look at PCl5. For PCl5, you will have P here at the central atom. At the axial positions, you will have a Cl and a Cl. And this is called as the equatorial position. So at the equatorial position, you will have 3Cl. You know what is axial and equatorial? You guys know what is axial and equatorial? You have a earth, right? Earth has what? North axis, north to south, you have an axis. And at the center, you have the equator. So whatever is here, that is your equatorial position. The top and the bottom, these are called as axial, right? Yes, Rekha, you had asked. So now this is your PCl5. Now tell me, what is the surrounding atom here? The number of surrounding atom is 5. Is there a lone pair? Do you see? No, nothing. That means what will it be? You will have 5 steric numbers. So 1s, P3 and D. Bas, that's it. That's it. sp3d hybridization. Okay. Next is NH3, bachus. Next is NH3. So for NH3, how do we draw the structure, guys? For NH3, what is it going to be? For NH3, you will have N here. a lone pair here and 3 hydrogen here. So this will be trigonal pyramidal. Trigonal pyramidal. Am I right? Yes, absolutely. Next, guys, HClO4. Acha, oh, HClO4 reminds me, we also have to do the strength of the acids, everybody. We also have to do strength of the acids. Sure. For HClO4, how do we draw it? So we will have Cl here, right? We will have Cl here. Then, actually, I need better space here. Chalo, let's do it for HClO4. HClO4, right? So you have Cl here. Now what you do is, see, surrounding atom, you have 4 here and you have 1 here as well. But how are we going to draw it? See here, double bond O here, okay? Then double bond O here, double bond O here, single bond O and H. Does that make sense? Does that make sense? Will you check the first question? Which was the first question, Bachu? This is the answer, okay? This is how you do it. And this will be in the shape of a tetrahedral, okay? This will have tetrahedral shape, okay? Chalo. Now, what do we have? We have H3PO4. H3PO4, guys. H3PO4. So, we will draw here P. Alright, yes, P. Double bond O here. And then what you do is H3PO4, right? So, OH. OH, OH. That's it. This will also be tetrahedral, okay? This will also be tetrahedral, guys. Next is NO3 minus. Chalo, let us do it for NO3 minus then. NO3 minus. How is it going to look, guys? NO3 minus, everybody. NO3 minus. Let's have a look at it. So we will have N here, okay? Then we know that there are oxygen. So we have 2 oxygen, let's write, and we can clearly see that there is 1 negative charge. So this 1 negative charge will go here. This oxygen will have 1 negative charge, and this is how they are bonded. Now see, 1, 2, 3, 4 and 5. All the 5 valency for nitrogen is done. Yeah. All the 5 valencies of nitrogen are covered. So here what will we have? Here the shape is going to be trigonal planar. We will have trigonal planar. Yes, great. Next, what do we have? SO4 2 minus. Acha, bachos, SO4 2 minus or H2SO4 if they ask, don't get worried. SO4 2 minus, if you remove the hydrogen, it will become SO4 2 minus. Okay. Alright, so let us write about SO4 2 minus. If you do, let's have a look at it. So you will have S here. Now you see there are 4 oxygens. So 1, 2, 3 and 4. Can I draw it like this? Yes, I can. Now I see that there are 2 oxygen. There are 2 negative charge, right? There are 2 negative charge. So I mean that these 2 negative charge will be shared by oxygen, right? So let me put it here. Let me put one here, and let's say that these ones will have negative charge. This and this oxygen are here. So obviously this will form a double bond and this will form a double bond. So here what will this happen? This will become tetrahedral. This will be tetrahedral. Am I clear, guys? Am I clear? Does this make sense, everybody? Does this make sense, guys? So if I give you homework now, will you all be able to do it? Yes? Yeah? This is clear? Chalo. Next, SF6, I have drawn it enough number of times. XEF2, I have drawn it, right? ASF5, that will also be trigonal bipyramidal. Now, will you all be able to do this homework, guys? Will you all be able to do this homework or not? Chalo, batao quickly, quickly, quickly. Quickly, will you all be able to do it or not? SF4? Yeah. Yes. No, this is SF6. Sorry, this is SF6. So SF6 will be octahedral. Okay, SF6 will be octahedral. Chalo guys, moving on. Let's solve another question here. The question is, explain why BF3 is a planar but NH3 is a not. I mean, come on, do we still have to do it? We know that what will happen is, in case of BF3, B is sp2 hybridized, isn't it? Yes, three surrounding atoms, no lone pair. This will be sp2 hybridized. So in case of sp2 hybridization, the geometry will obviously be trigonal. Geometry will obviously be trigonal planar, right? Yes, the geometry is going to be trigonal planar. Now they are also talking about NH3. For NH3, what will happen? For NH3, it will not just be, the steric number is going to be 4 because there are 3 surrounding atom plus 1 lone pair. It will be sp3 hybridization, and sp3 hybridization geometry is tetrahedral. However, there is also a lone pair, so what will happen? It will become trigonal pyramidal. Yes, trigonal pyramidal. Okay, all right. Yes, absolutely right, bacha. Absolutely right. Now, second one. Read the question. CCl4 and SiCl4 are tetrahedral. Obviously. Look at C here. Carbon here will be able to form only 4 bonds, right? So 4 surrounding atoms. Done. It will be what? sp3 hybridization. sp3 hybridization for CCl4, SiCl4. Chemistry, sir. Carbon, then silicon. Silicon will also have 4 electrons in the outermost shell, isn't it? So silicon will also have 4 surrounding atom. The valence shell electrons are done. That means this will also be sp3 hybridization. Hence, the molecule geometry will be tetrahedral. So, is this simple? Is this simple, everybody? Very good. Well done, guys. Chalo. So now we have understood. Next question. The state of hybridization of the central atom is not the same as in the others. Can we tell? Can we tell everybody what is the answer, guys? What is the answer? What is the answer? Here, chalo. For BF3, B in BF3, the state of hybridization of the central atom. So B in BF3 is sp2 hybridized, isn't it? O in H3O plus. O has, see, O plus, right? O plus, that means HHH. Now, oxygen has how many electrons? Oxygen has 6 electrons. But here, 3 electrons are over. It will still have a lone pair, and see, it says O plus. So 1 electron is given away, but it will still have 5 electrons, right? So now does it make sense? So this will be sp3 hybridization, isn't it? This will be sp3 hybridization. Now, N in NH, no, this will be NH3, guys. This will be NH3, okay? This will be NH3. If it is NH3, then what will happen? Then we will have similar sp3 hybridization. P in PCl3 will also have sp3 hybridization. So our correct answer is option A. Option A. Right, everybody? Are we clear? Yes. Kumar, you are absolutely right, guys. Absolutely right. Chalo. Next question. Find the molecule with the least bond angle. Guys, BeF2. BeF2 will have 180 degree. CH4 tetrahedral 120 degree. SF6, it is octahedral. Octahedral will have 90 degree. BF3 will also have 120 degree. That means our SF6 is the correct answer. SF6 is the correct answer. Right, guys? Right. Yeah. EPBT, very good. Okay, next question. In a regular octahedral molecule, read this. MX6, the number of XMX bond at 180 degree is. That means they are saying that we have M here, and then we have X, and X, right? Like this. So, how many 180 degree? How many XMX? So, we have XMX here, 180 degree. 1. We have XMX here, 180 degree. Another one. Yes, and we have XMX here, 180 degree, another one. That means that the answer is 3. Option A is the correct answer. Am I right, everybody? Please have a look and let me know. Please have a look and let me know. Is this correct? Yeah, there are 3 of them, right? There are 3 of them. Very good. Okay. Alrighty, everybody. So now we are done with VSEPR theory, right? VSEPR theory. We are also done with hybridization. But what we are not done with is valence bond theory, right? We are not done with valence bond theory. Should we just quickly go through valence bond theory just for a little bit, because I believe that we already know valence bond theory, and I have recently taught you valence bond theory. If you remember, everybody. Do you remember? I've taught you valence bond theory even in your, what was it? In your coordination compound, right? I've taught you valence bond theory. So let's quickly go through valence bond theory just a little bit, and then we will move on towards our molecular orbital theory. Also, we do not have much time, guys. Yeah, acid strength I'll teach you. Don't worry. Acid strength I'll teach you. Don't worry. I'll do that. Yes. Here we go. Yeah. Here we come towards valence bond theory, everybody. Now see, remember I was teaching you about that how if two hydrogen atoms, do you remember that I drew like this one? Okay, here let me write here VBT. VBT you all know, right? VBT is valence bond theory. So let's say that we have one hydrogen atom here. There is another hydrogen atom here, right? Now what will happen is, let's say that this atom now comes closer. When it comes closer here, what will happen, guys? Here when it comes closer, what will happen? Anybody? Any idea what will happen when this comes closer, guys? When this comes closer, you have to understand, everybody, that here basically what is happening. Any idea? People? Any idea? Can somebody tell me what is happening here? No one? No one? No one? Yes? Come on, guys. Somebody reply. Bonding. Yeah, finally. Uffo. Bonding you are not able to tell me. Huh? Bonding you are not able to tell me. You guys. Pity. Virtual punch you will get. There will be bonding. Then there will be repulsion as well as attraction. So when this atom comes closer, everybody have a look. When this atom comes closer, there will definitely be some merging, that is overlapping, right? This will come like this. See, this will come like this. So there will be overlapping here. There will be overlapping, right? Are you guys understanding? So there will be overlapping. So when overlapping happens here, you understand that the bond has formed. Now you have to understand that when these two were separate, right? These two were separate. This is called as an atomic orbital. This is also called as an atomic orbital. But the moment this one, I take this one and I put it like this here, after merging this atomic orbital and the second atomic orbital together, what do they form? They form these two, okay, one second. Together, they form a molecular orbital. Now, actually what happens is, if you want a graphical representation, okay, if you want to have a look at a graphical representation, what happens is, one second, sorry guys, this is not the way to, right? This is, imagine that this is a graph. This is also not a straight line. One second. Why am I not able to draw a straight line, guys? What is this? This is meta. Still, somehow it is a straight line, isn't it? Somehow it is a straight line. So now here, let's say, assume that this is our R, okay? This is our R, okay? This is R. So what happens is, everybody, and let's say that this is our potential energy. Yeah. So when you, let's say that the atom was here, right? The atom was here. Okay, and there was another atom that was here. Okay, these two were not very close, obviously. These two were not so close. So these atoms, when together they came here. Okay, together they came here. Okay, what happened here? Here the bonding happened. After that, what happens is, this goes up. After that, if you try to bring them closer, if you try to bring them more closer, okay, see, I was explaining you like this, right? So here you had this atom. If I try to bring this even more closer, now what will happen? The stability will be disrupted. The stability will be disrupted, everybody. At certain point, yes, at certain point, so when they are far away, it is less stable. The bond length is also huge, right? The bond length is also huge. Then they come together, it is more stable. Smaller is the bond angle, smaller is the bond length. Now if you try to bring them even more closer, yes, it will be stable. With maximum overlapping, when the overlapping is maximum, the bond length, the bond strength is also maximum, right? Yes, the bond strength is also maximum. With the maximum overlapping, it will be great. But you have to understand that with after there is only a, you have to understand, so the overlapping, let's say the overlapping cannot be complete, right? It cannot be complete overlapping. Why? Electron repulsion will also happen, right? Electron repulsion will also happen, isn't it? Yes. So when there is a bond formation, the energy is the least, everybody. The energy is the least. Now if you want to break this, you will have to give this energy. You will have to give this much energy to break it. You will have to give this much energy to break the bond. You have to understand that when they have overlapped here, what is happening? The energy is less. If energy is less, that means it is stable. If energy is more, then that means that is not stable, right? Yes. So everybody, am I making sense? Am I making sense? Yes. Exactly, ma'am. Like it's said to be stable, like an equilibrium state, but we define the bond to be a force of attraction. Yeah. We define the bond to be a force of attraction because there is an attraction that is in picture. There is an attraction that is in picture. And because of this attraction only, the overlapping is happening. Once the overlapping is happening, after that it comes in an equilibrium state. But first, the first and the foremost thing that happens is it's a force of attraction. Getting my point? Do you understand now? Yes? Do you understand now? Someone new? I think I've explained your doubt. Right? Now, everybody, this particular point, okay, this will be called as your bond length. This will be called as your bond length. Are you understanding, everyone? Yes, are you understanding? Cool. Acha. Now, let us understand the orbital overlap, okay? Let's understand the different types of orbital overlap. Orbital overlap types. Okay, this will make your phase and orientation, yes, phase and orientation, that will be clear. Now phase, you know, positive overlap, in phase overlap, otherwise a negative overlap, out of phase overlap, and then there is zero overlap as well, right? So chalo, let us have a look at that one by one, everybody. Okay, let us have a look at that one by one, everyone. Firstly, let us talk about positive overlap. Okay, positive overlap, but choose positive overlap is called as in phase overlap. What is this? In phase overlap. Okay, all right. Now in case of in phase overlap, let's have a look at your p orbital. See, this is your p orbital, let's say, and this is another p orbital, let's say. Okay, all right. So everybody, do you understand that if you have a here minus sign and if you have another minus sign here but plus and plus here, so this will be called as an in phase overlap. What will be this called? This will be called as in phase overlap. Now there will be another in phase overlap which will look like this. So this, and here you have this and this. Now let's say if these two overlap, and let's say here you have a plus, here you have a plus, here minus, and here minus. So plus and plus together, minus and minus together, what will you have? You will have in phase overlap. Please understand that this positive and the negative sign, this does not denote anything to do with charges. This is nothing to do with charges. The charge will obviously be negative because we are still talking about electrons here, right? Yes, we are still talking about electrons here. This is only a phase. This only denotes a phase, okay? That means similar interaction. That's all that we are talking about. Understanding, everybody? Thank you so much, Cryo King. Thank you so much. Yes, do we understand this? Now, let us talk about negative overlap. Okay, guys, let's talk about negative overlap. What is this negative overlap? Negative overlap means out of phase. Okay, what is it? Out of phase overlap. Okay, out of phase overlap. Everybody have a look. Let's say that we have a p orbital here like this, another p orbital here like this. These two, when they want to come together, understand this everybody, have a look here. See, let's say this is positive, this is negative, but this is negative and this is positive. Now what will happen? These two are out of phase. Okay, these two are out of phase, and similarly if you just turn it around, you will again get another out of phase. Acha, now you all know what is the shape of s orbital, guys. What is the shape of s orbital? Everybody, do you all know what is the shape of s orbital? S orbital is spherical in shape, right? So a spherical in shape, and if there is a p orbital, if these two come together, where is the overlapping going to happen? Will there be any overlapping? Will there be any overlapping? Okay, understand this what I'm trying to tell you. I am basically trying to tell you zero overlap. Okay, zero overlap means there is hardly any interaction. That means there is no interaction. So here, let's say that we have a p orbital like this and we have an s orbital. So together, if these two come, okay, now tell me, let me try and show you how will these two overlap. Okay, or will there even be any overlap? Is there any overlap, guys? Do you see any overlap here? Is it overlapping at all? In fact, right here, if you see, right here, there is a gap. Right here, there is a gap. Have a look, everybody. Once again, I'm going to bring this closer here. If I bring this closer, do you see here you have a gap? Here you will have a gap. Actually, yes. So this is what I'm talking about. This is called as zero overlap. If it is not a head-on collision, then there might be zero overlap. This is what? Side by side. This is side by side, right? So this is not called as, this is not, there is no overlapping. Okay. All right. Now, based on overlapping, everybody, based on overlapping, we have sigma bond, we have pi bond, we have delta bond also. Yes, we have sigma bond, we have pi bond, and we have delta bond as well. So let us try to figure that out. Yes. So let us first talk about what is it? What did I say? Bond based on type of overlapping. Bonds based on type of overlapping. Okay, so now let us first talk about sigma bond. In sigma bond, you have to remember one thing, that is one lobe interaction. In sigma bond, what do you have? In sigma bond, you have one lobe interaction, everybody. For example, sigma bond we are talking about, right? For sigma bond, you will have s orbital and s orbital interaction. You will have s orbital and p orbital interaction. You can also have p orbital and another p orbital interaction. All right, you can have d orbital, dz square, and another dz square interaction. This will also be head-on collision, right? This will also be head-on collision. So this will also get you a sigma bond. Are you getting my point, everybody? Are you getting my point? Now here there are 2 to 3 things that you remember. All single bonds are sigma bonds. Sigma bonds always go for head-on overlapping of bond, and it is a strong bond. Okay, it will be the strong bond. Clear? Hey everybody, is this clear, guys? Is this clear? Yes. Is this clear? All right. Yes. Chalo. Moving on. Now let us talk about pi bond here. Okay. Let us talk about pi bond here, everybody. For pi bond is a sideways overlapping. So for example, let's say that this is my z axis, this is my z axis. If this is my z axis, that means that let me say that this is my y axis and this is also my y axis here, right? Now if I have py, this is my py, this is also my py. Now what we notice is, okay, what we notice, everybody, is Right here you get a saucer shaped interaction. Right here also you get a saucer shaped interaction. So this becomes a two lobe interaction. What does this become? This becomes a two lobe interaction. The axes remain parallel, but here, right here, yes, they are also perpendicular to the z axis. Do you understand this? Do you understand this? And right at this position, everybody, chalo, let us try to understand this. Right here, okay, right here, if I put a plane, do you think that you will find do you think that you will find any electron right here? If I put a plane right here, will I be able to find any electrons? No. The electrons are here and here. These two saucer shape, like a plate shape, isn't it? These two are plate shape, है ना? Saucer shape clouds of electron you will find, but if you put a plane here, which is called as a nodal plane, you will not be able to find any electron. You will not be able to find any electron. Am I clear, guys? Yes? Am I clear, everybody? Do you understand? Yes. So pi bond mostly is found in p orbital. But tell me something, everybody. Tell me something, guys. Tell me something. Do you think that d orbitals, what will d orbitals do? D orbitals can also show pi bond, pi bond, right? D orbitals will also be able to show you pi bond, isn't it? Isn't it? Chalo, let's see. Okay, let's see that here. Sorry, by mistake. Let's go back here. Let's go back here. Let's say that here we have a axis. Okay, z axis. Okay, z axis. Now if I have, okay, okay. Okay. Now see, this one will try to form a bond with this. Okay. This one will interact like this. Then here, this will interact like this here, and this will interact like this here. No, that will be delta bond. Sorry. That will be delta bond. एक second guys, एक second. Here you will again see that this and this, so two lobe interaction here, you will once again be able to see a pi bond. Now let's talk about delta bond. Okay, now let us talk about delta bond, shall we, guys? Let us talk about delta bond, guys. When do you see delta bond? Delta bond is formed when there is a four lobe interaction. Okay, yes, four lobe interaction. So let's have a look, everybody. Let's have a look at delta bond. Yeah, delta bond, guys. For delta bond, let's say that we have our z axis here. Okay, this is our z axis. Let's make an axial. Okay, let's make an axial d orbital, that is dxy. Okay, what is this? This is dx square minus y square. Here, do you see that this one will interact with this? Here, this will interact with this. This will interact with this, and this will interact with this. So four lobes, when they are interacting with each other, you will get a delta bond. You will get a delta bond, everybody. Yes, like for example, see, this is your z axis, right? Everybody understand it. Chalo, understand it. This is your z axis. Here what you have done is, this is your lobe here, and this is another d orbital. So these two are, when they are reacting, they are reacting like this. Okay, they're sorry, not reacting, interacting like this. So understand it, that imagine that these are the four d orbital lobes. So they are interacting with each other like this. Okay, they are interacting with each other like this, and this is your delta bond. Bachu, bro, where are you from? Which class are you from? Anuradha, you have your exam in 24th of January, bache. If you are asking me lobe meaning, then either you are not appearing for the exam, or I do not know what to say. Yeah. Okay. Chalo. So everybody, have we understood sigma, pi and delta bond? Have we understood sigma, pi and delta bond, guys? Have we understood sigma, pi and delta bond? Please tell me. Please tell me, have we understood sigma, pi and delta bond? Yes or no? Yes or no? Yes? Facing toward each other. Yes, facing toward each other. Now, can I get some EPBT in the chat box? Do I get some EPBT in the chat box? Yes? Can I get some EPBT in the chat box, everybody? Come on. Acha, while we have done the sigma and pi bond, you have to understand that sigma bond is stronger, pi bond is slightly weaker. Yes, free rotation is not possible in case of pi bond, free rotation is possible in case of sigma bond, and obviously sigma bond is the strongest, the delta bond free rotation is even more not possible, right? All the differences and everything, I believe that you already know it and I do not have to teach you. Do I have to teach you? I don't. Now, let us talk about something called as a number of p-pi bonds and number of d-pi bonds. Are you all with me? Let us talk about number of p-pi bonds and number of d-pi p-pi bonds. All right, shall we talk about this, guys? Hey! What are you guys doing, huh? Talking about something and all that is not related to the class. Guys, pay attention here. Pay attention. You all are only telling, no, that ma'am, this is getting difficult, that is getting difficult. Then why are you doing this? Why are you doing this? Study properly. Huh? Study properly. RGS Telugu Gaming. Sweetheart, pay attention. Pihu, pay attention. Please pay attention, everybody. Acha, for number of p-pi d-pi bonds, how about let us take the example of xenon XeO4. Let us take the example of XeO4. Okay? Now, in XeO4, let us draw the structure. Okay, the structure I have already taught you how to draw, right? You have to find the hybridization, you have to find the steric number, and then you find the hybridization, then you draw the structure. So here you will have double bond O, double bond O, double bond O, and double bond O. Now tell me, oxygen belongs to which period? Oxygen belongs to second period. A second period element cannot have a d orbital. Am I right? Yes. Yes, everybody. A second period element cannot have a d orbital. We all know that. We have learnt about it in P block many number of times, that in the second period element, that is boron, carbon, nitrogen, oxygen, fluorine, all of them, they have anomalous properties. Why? Absence of d orbital. So these guys, whenever they are forming a bond, what are they going to do? They are going to give only their p orbitals, right? They can only provide s orbital and p orbital. They do not have anything else to provide, isn't it? They do not have anything else to provide. Do we understand this? But xenon, however, xenon belongs to what? Helium, neon, argon, krypton, xenon. Xenon is way at the bottom. So xenon definitely has p orbitals as well as d orbitals that it is going to provide. So that means that now xenon, what will it do is, what is the hybridization, everybody? What is the hybridization? We can clearly see that there are surrounding में four atoms in surrounding. That means steric number 4. Steric number 4 बोले तो sp3 hybridization. So that means xenon has definitely given all its p orbitals. Okay, s plus p plus p plus, there will be d orbitals as well for xenon, right? There will be, let's say, since it's forming 4 bonds, so there are 4 d orbitals. So sp3, all of these have hybridized. All of these, all the p orbitals that you have for xenon, they have hybridized. So there are 4 sigma bonds, right? There are 4 sigma bonds. This is a sigma, this is a sigma, this is a sigma, this is a sigma. But there are also 4 pi bonds. These 4 pi bonds, oxygen will obviously always give you a p orbital to form the bond. There will be p pi here, and it will give you a p pi. But xenon, see, xenon does not have any more p orbital only. Xenon does not have any more p orbital. So what xenon does is xenon gives its d orbital. So it will give you d pi, d pi, d pi and d pi. So here how many p pi d pi bonds do you have? You have 4 p pi d pi bonds and you have 4 sigma bonds. So do we understand this? Do we understand this, everybody? Do we understand this? Chalo, let me give you another example, okay? Let me give you another example, everybody. How about, because I want it to be a little more tough so that we understand this. SO2. No, SO3. Let's take the example of SO3, everybody. If I take the example of SO3, okay, for SO3, there is no charge. So S, double bond O, and double bond O. Surrounding atom is 3. There are no lone pairs. So what is the hybridization, guys? Steric number is 3. If steric number is 3, then sulfur here is sp2 hybridized, isn't it? Sulfur here is sp2 hybridized. So that means that we have S plus P plus P plus P. There are 3. And then there are D, 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 D and D. There are 5 D orbitals and 3 P orbitals and 1 S orbital, right? So sp2 went for hybridization. The 3 sigma bonds that you see, they are from sp2 hybridization. But you see that there are also pi bonds. There are 3 pi bonds. Now what sulfur will do is, the first pi bond that it is going to form, sulfur here will give you a p pi. Oxygen has no other option but to give you a p pi. So there will be a p pi bond. Now sulfur does not have any more p orbital, right? So this p orbital is done. This p orbital is also done. Once this is done, now sulfur has no other option but to provide a d pi, and oxygen again will give you p pi. Sulfur will again give you d pi, oxygen will give you p pi. So here all of them, now do you understand? So now you have 1 p pi bond and 2 p pi d pi bond. Now tell me, is this easy? Is this easy? Is this easy? Cryo King, I think I have already explained to you how to draw the structure. Please do the honor of making the structure on your own. Yes, how to, Yogi, I have already explained, bacha. Before this, I have started the session at 6 p.m. You were not here. I have started the session at 6 p.m. everybody. In between, my internet internet was switched off, so I had to make another stream key and take it, but I have already done it. So please watch the session from the beginning, the previous session, so that you understand everything. Okay? Is this clear, guys? Is this clear, everybody? Do we understand this? Do we understand this, everyone? So easy, exactly, so easy. But so many students make a mistake when they are calculating S and P pi and D pi. Chalo. Now we have to understand percentage S character. Shall we, guys? Shall we? Let us quickly understand percentage S character, and after that we will directly go to molecular orbital theory. Okay, we have to be a little faster, guys. We have to be a little fast, everybody. Yes, percentage S character. What is this? Percentage S character. All right. Acha, what is percentage S character? So now when we have, let's say that there is one S orbital. If we have just one S orbital, okay. If you have just one S orbital, then what is going to be the percentage S character? Obviously 100%, right? S orbital looks like this, correct? Very good. Now, if I have just one p orbital, then what is going to be the percentage S character? Is there any S orbital? Is there any characteristic of S orbital? Do you see? Nothing. So this will be 0%. P orbital looks like this. Okay. Now let's say that we have a hybridized sp orbital. If it is an sp hybridized, then what will happen now? 50% from S, 50% from P will interact. So we will have percentage S character to be 50%. Make sense? Make sense? Very good. Now if I have sp2, so guys understand, 3 people are sharing and forming a bond. 3 people, okay, let's say, acha, chalo, okay, everybody, okay, explain again. Vamsi Krishna, explain again. Chalo, let's understand this, everybody. Forget about all of this that I have taught you. If I have 100 rupee, let's say I have 100 rupee. 100 rupee is equal to 100% S character, okay? 100 rupee, 100%, okay? 100 rupee, if I have to give it to, let's say, Vamsi. Vamsi is the only student in my class. Let's say that I have only one student in my class and I have to give 100 rupee. Then who will get? Who will get it? Vamsi will get all the 100%, right? So S character here is 100%. Yes? Great. Now, let's say that I have a student in my class but I do not have 100 rupee. What will I give? 0. I will give 0. So, in case if I have a p orbital, so p orbital means yes, I have a student but I do not have the rupees to give. I do not have the rupee to give, hence it will be 0%. Yes, now let's say that I have 2 students. I have Pranav and I have, let's say, Kanishk Goli. I have Pranav and Kanishk Goli. I have 2 students in my class and I have 100%. How do I divide it? How do I divide it, bachus? 50%, 50%, 50 rupee, 50 rupee, right? So if there is an S and P hybridization, then what will happen? Percentage as character will be 50%, 50%, right? Very good. Okay. Now let's say that I have 3 students. The 3 students here are, let's say, Shri Chandana Akkala. Okay, then we have Chandra Mohan Shivanandan, and we have let's say Aryan Kumar. Okay, so we have Aryan, Chandra Mohan, and we have Shri Chandana. Now I have 3 students. If I have 3 students, 100 rupees, how do I divide? How do I divide the 30%? Sorry, how do I divide 100 rupees? 33.33, 33.33, 33.33. It will get me 99.99999%. Do you understand? So here 3 students, it will be 33%, right? It will be 33%, 33.33%, whatever you want to say, write it down. Okay. Now if I have 100 rupee but I have 4 students, guys, I have 4 students, everybody. Now how will I divide it, everybody? Now how will I divide it? I will divide it as 25%. 25 rupee, 25 rupee, 25 rupee, 25 rupee. Do we understand this? Is this clear? Any doubt here? Any doubt here, guys? Any doubt here, everybody? So if it is S and P orbital, then what will happen? You will have P like this and here will be the S hybridization, isn't it? Here will be the S. If you have sp2, then it will be like this, it will go like this, and here will be your S, right? If it is sp3, then this will be this will be long, and here it will be. So understand this, if percentage S character increases, then bond length decreases, okay? Bond length decreases. If percentage S character decreases, bond length increases. Understanding this, everybody? Understanding this, everyone? Yes? What for sp3d? Pranav, you tell me. You tell me, if I have to divide the money in 5 people, now what will I do? 20, 20, 20%, isn't it? I will be dividing it in 20, 20, 20%. That's it. That's it. If there is percentage as character, acha, now there is also something called as electronegativity. They may ask you, percentage as character, if it increases, electronegativity increases. Why? Because you can see here, okay, check it out, guys, check it out. Right here, everybody, right here, do you see that this right here is closer to the nucleus? This S orbital is closer to the nucleus, whereas this S orbital is farther away from the nucleus. This is the farthest away from the nucleus, so electronegativity increases when percentage S character increases. Do we understand this? Do we understand this, everybody? Yes, we do. Yes, we do, isn't it? Chalo, great. Now, one last thing that I have to teach you before we move on to molecular orbital theory, and that is your, what was it? Acidic strength. Yes, acidic strength. Chalo, let us take the example of HClO4. Okay. Then let us take it as HClO3. Okay. Then we have HClO2 and we have HClO. Okay. If that is the case, what you're going to do is you're going to find the conjugate base. These are all acids, okay? These are all acids. Find out the conjugate base. How do you do that? Nothing. Just dissociate the hydrogen from here. You will get ClO4 minus. Then you will get ClO3 minus. Then you will get ClO2 minus. And finally, you will have ClO minus, okay? Now, what we're going to do is we're going to draw the structures here, okay? Yes, we are going to understand the structure here. Vamsi, please just rewind it and watch it again. But just rewind it and watch it again. I think you will be able to understand, okay? If I go back again, 8:40 it is already. I have to also finish molecular orbital theory and it's very essential. Let's quickly go through this, okay? At 9 p.m. sir is going to take class. So you have Cl here, okay? Then you have double bond O, double bond O, double bond O, and this one will have a single bond O here minus. Now when this minus comes here, okay, this minus comes here, what will happen is from here the double bond will get up, and then as you go ahead, this negative charge will actually be distributed among the whole molecule. Yes, this negative charge will be distributed among the whole molecule. Hence what will happen is this will be very stable. You know that, right? When somebody has much high charge, it will be super reactive. It would want to react. But if it does not have so much charge, if it is distributing among itself, it's going to be stable. It's going to be stable, isn't it? So exactly that's what happens. Now, if I want to draw it for ClO3 minus, now what will happen is I will have Cl here, and then let's say you have a double bond O here, double bond O here, and one single bond here. Now the molecule has become a little smaller, and I can clearly see that this will be distributed in a smaller area. And similarly, as you go down, the area will become less and less and less. For example, for ClO minus, there will be one single bond that is formed here. Yes, and Cl will still have 1, 2, 3, 4, 5, and 6. Correct? Yes. Are you understanding, everybody? So the acidic strength will be the highest for HClO4, then it will be for HClO3, then it will be for HClO2, and then finally it will be HClO. Why? Because as this is already, understand this guys, please understand this, everybody have a look, as this molecule, this HClO4 minus, because of the resonance, because of what is happening, the charge is getting distributed among the whole molecule, so it is happy on its own. That means that it does not want to accept more hydrogen ions, hence hydrogen ions will be released, and that means that they are good acids, right? That means that they are good acids. Am I right? If somebody releases H plus ion, that means that they are a very good acid. Correct? Am I right or wrong, guys? Am I right or wrong? Quickly tell me, everybody. Quickly tell me, am I right or wrong? What I'm explaining it to you, do you understand this or not, everybody? Yes, no, nobody is saying anything. Yes, Chandra Mohan says yes, ma'am. Okay, so that's it. Yes, now let us quickly go to molecular orbital theory, everybody. In molecular orbital theory, why did we have a molecular orbital theory? Because once again, all the other previous theories failed, right? So molecular orbital theory, it is formed by combinations of atomic orbital. I think that's something that I already explained. If you combine atomic orbitals, once you have combined atomic orbital, one atomic orbital, now is it still an atom? No, Baba, it is a molecule. So atomic orbital combined, and they have formed a molecular orbital. So this is how you form molecular orbital, right? So now do you remember that when they overlap, the overlapping has happened, merging has happened, where at that point, where they are overlapping, right at that point, the electron density is maximum. Do we all agree? Do we all agree? Do we all agree or not? See, what I'm trying to explain it to you is, if this is an electron and if this is an atomic orbital and if this is another atomic orbital, right at this place I am expecting to find electrons, isn't it? Right at this point I am expecting to find more electron. So here my electron density is going to be high, and this particular place is called as a bonding molecular orbital. What do you call it? You call it as bonding molecular orbital. Clear? So if we have a bonding molecular orbital, then do you remember in all the other cases we have said, even in hybridization we have said, do you remember that if I mix 1 glass of milk, 1 ice cream, I should be getting 2 glasses of milkshake, right? That's what I explained. Am I right? That's how I explained. Whoever is taking part, if there is 2 plus 2 taking part, then I must have 4 hybridized orbitals, right? If I have 3 plus 3, then I must have 6 hybridized orbitals. But here, when 2 atomic orbitals are merging, I'm getting only 1 bonding molecular orbital. My God, where is the other one? How is that possible? If 2 people are getting mixed up together, this is not a possibility. This cannot be possible that I get only 1 bonding molecular orbital. I must get another one. But what is happening? Where is that? This is where we bring in, we borrow a little bit from Shreyas sir, a little bit of physics from Shreyas sir, and let us talk about this. Have you read about constructive interference and destructive interference, everybody? I know you have. I know you have. Yes? Wave nature, isn't it? When we talk about the wave nature, isn't it? Wave nature. Where do we talk about this? Where do we talk about this? Constructive interference, destructive interference. Isn't it that Young's modulus, right? Do you talk about Young's modulus? Was it in the Young's modulus experiment? No. You do something with the laser light, isn't it? You do something with the laser light, and that's when you see the constructive interference, and then there is this. Anyway, forget about my physics. Who cares about my physics? Anyway, so what happens is when 2 atomic orbitals are in phase, what will happen? Constructive interference. Wave optics. Yes, you talk about it in wave optics. So in wave optics, you see that if two waves are in phase, then you get a constructive interference. Yes, but if the waves are not in phase, if they are in opposite phases, then what will happen? They will not give you anything. So basically that is what is happening. When they are overlapping, you get a bonding molecular orbital, but the out of phase thing that is happening, that gives you an anti-bonding molecular orbital, guys. So that means every time 2 atomic orbitals are mixing up, they are giving you 2 molecular orbital. One is bonding molecular orbital, the other one is anti-bonding molecular orbital. So the destructive and the constructive interference somewhat looks like this. So if it is constructive, everybody, if it is constructive, bachus, then what do we get? If it is constructive, then you see something like this. Let's say these are 2 waves, so you will have 1, 2, like this, right? Like this. See? Similar. But if it is destructive, okay? If it is destructive, then what will happen is, see, if it is destructive, then you will have 2 waves such as this. One will be, let's say, like this, and the other one will be like this. Now that they are opposite, they will cancel out each other, and we will be left with nothing. We will be left with nothing. So this is your basically the nodal surface. Remember in p orbital I was telling you that if this is my nodal plane, my chances of finding an electron here is 0. Exactly. So that is your anti-bonding molecular orbital. Now obviously molecular orbital theory that we are going to study, right, which we are studying right now, it depends on the same thing that we have read about, Pauli's, Hund's and Obbo. These 3 principles are what we follow for our molecular orbital theory. Okay? Yes, everybody. Do you understand? And do you remember in the atomic structure, do you remember, everybody, we read about Schrodinger's equation? Yes, and there was that trinity kind of a sign, psi there was. Yes, this A and this B that we read about. Exactly. So there is also a theory that is called as linear combination of atomic theory. Okay. Yes, there is also something called as a linear combination of atomic orbitals, LCAO. In that, when we talk about constructive interference, our bonding orbital, bonding molecular orbital sigma is equal to psi A plus psi B. Destructive interference, after destructive interference, this you get sigma star, where psi A minus psi B takes place. So this is called as anti-bonding. Okay, this is called as anti-bonding, everybody. Am I clear, guys? Am I clear? Am I clear? Now, molecular orbital theory was great because it could also predict the molecular behavior. It could tell us about stability. It could tell us about bond order. It could tell us about nature of bond. It could tell us about magnetic character, and it could tell us about the bond length as well, everybody. It could tell us about the bond length as well. So see, this is what I was teaching you. Linear combination of atomic orbital. A lot of it is written, but I hope that you understand what is linear combination of atomic orbital. Just told you, constructive interference, destructive interference. Constructive interference, psi A plus psi B. When you solve all the Schrodinger equation, but you don't have to. I mean, that's out of syllabus. If it is destructive interference, what do you do? Psi A minus psi B. Okay, minus psi B. That's it. That's it. See, guys, this is it. This is what you study, right? Okay. Okay. Okay, let's say that. So basically, okay, these two are similar. These two are similar. So similar things will add up like this, and now see, the height has increased. Okay, now you may tell me that, oh ma'am, the height of the bond has increased like this. But if it was ulta, then see, now what is happening? Now what is happening? Like this. Now here you don't see a bond, right? Here you don't see a bond. Actually, this is not the right example. I don't have anything to show it to you exactly, but acha, chalo, look at this only. See, look at these two waves. Okay, see, this wave and this wave, are they both similar, guys? Are they both similar? They're similar. So what will happen is they will add each other up, and see, the amplitude has increased here. Amplitude. What is amplitude? Amplitude is the maximum distance that the wave has got up to. That is the length of the wave. The length of the wave is called as amplitude. See, the amplitude is increased. Amplitude has increased. But if it is a destructive interference, see, now if it is a destructive interference, if these two are not similar, then what will happen is, it will not even show. There will not be any curve at all. Anupam Raj, now do you understand? Now do you understand, everybody? So this is how we represent molecular orbital theory. So that way, psi A, that is your atomic orbital. Right here, psi B, this is your atomic orbital. Together, they form a bond here. Now guys, understand this. When there is constructive interference, there is bonding, overlapping. And I showed you, right? Overlapping means what happens? Energy becomes less. If energy is less, then what will happen? Stability will increase. So here, energy is less. But anti-bonding does not exist. Anti-bonding will have higher energy. So anti-bonding, you keep it up. This is your anti-bonding. This is your bonding molecular orbital. This is your anti-bonding molecular orbital. Do we make sense? Are we clear, guys? Are we clear, everybody? Chalo, let's do one or two questions and then I will let you go, because that's it. That's it, okay? That's it, guys. That's it. Now, chalo, let's do one question. Okay. During the change of O2 to O2 minus, the incoming electron goes to the orbital. Okay, this is going to be easy. Stability increases. Yes. This is going to be easy. I believe that you will all be able to do it. But chalo, let me show you, guys. How do we draw the molecular orbital? Easy peasy way, I will tell you. I'll tell you easy peasy way, okay? Always do one thing. You should always draw 1, 2, 3, 4, okay? After that, fifth one, then 1, 2, then 2, and then 1. Now what do you do? Now you write here sigma 1s, sigma 1s, sigma 2s, sigma 2s, sigma 2pz. Then you write here pi 2px and pi 2py, pi 2px. See, I'm repeating the same thing. Do you see, guys? I'm repeating the same thing. And then here you write sigma 2pz. Now what you have to do is, whatever I have written on the top, make that a star. Sigma star 1s, sigma star 2s, sigma pi star 2px, pi star 2py, sigma star 2pz. Do you understand this? Do you see what I have done? Now, for oxygen, oxygen will have how many electrons, guys? Oxygen will have 8 plus 8, 16 electrons, isn't it? Oxygen will have 8 plus 8, 16 electron. So 16 electron, everybody, have a look here. How do I fill it? You will fill it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. Done. Now they are saying this is O2 negative. There will be another electron that will be coming. Now this another electron, where will it go? It will go here, pi 2px, right? Pi star 2px. That's where it will go. So it will be option C, isn't it? Option C is the correct answer. Pi star 2px. Yes, option C, pi star 2px is your correct answer. So guys, now I'm going to stop the class, everybody. Yes, there are the weak bonding that is left. I could not do it. I could not finish it. But nothing to worry about. We will very soon meet you and I'll be providing you with the PDF and everything, everybody. You all know that you also get DPPs. That is, what do you get? What do you get, guys? You also get daily practice paper, and that will be just below this video, everybody. Let me take a look at it. Yeah, 1, 2, 2, 1. That is for more than 40 number of electrons. Okay, Pranav, more than 40 number of electrons is 1, 2, 2, 1. If it is less than 14 electrons, 2, 1, 2, 1. Okay. Alright guys, let me quickly show it to you that this is where you can have a look at your daily practice paper, because we do provide you daily practice paper. And where is my class? Where is my class? JEE English. Yeah. Here is my class.
Welcome to the My Tiles Experience Center, Bangalore. We are the largest tile store in town, offering an exclusive and premium range of imported wall and floor tiles. Step into a world of elegance and discover the perfect tile for your space. Can't make it to the store? No worries.
Do join it with this note. Thank you so much. Thank you so much for supporting me twice today. Had to take the session twice. I'll see you very soon. All the very best and lots of love. Do study this chapter. It's very important. I have taken care of majority of the tough part of the chapter, but you also have certain bit of hydrogen bonding and van der Waals forces that is left. But don't worry about it. Majority of the question actually comes from hybridization, molecular orbital, VSEPR and VBT. Study them properly. I think you will be able to do it. It is going to be amazing. And stay here now. Stay here. Because Shreya sir is coming up with his session, everybody. So tata, bye bye. I'll see you all very, very soon. And